you were the thing you wanted to talk about, or you mentioned before in the CV that you gave me, was about the formation of how black holes and what they have to do with the formation of the universe. Is that correct?
Yeah. So I think one of like the most interesting questions is what role do black holes play in structure formation?
Yes.
And in what role they play kind of like in the life cycle of the universe.
Like a supermassive black hole in the middle of a galaxy, like that type of thing?
Yeah, so imagine every galaxy has this supermassive black hole at its center. And kind of what they act as is the engine for the entire galaxy. So it's basically like a blender that recycles all the gas that's in the galaxy. So basically, you'll have some gas that falls into the black hole and some that gets shot out.
Yeah.
And that gas that gets shot out, it's going to be used to generate the next generation of stars.
Okay.
And so if we want to understand, like we were talking earlier about like planet formation and like what kind of like elements you have like available to make the next generation of stars and the next generation of solar systems, you have to understand what's the gas that's available. And if you want to understand that, you want to see how much of the gas was recycled by these AGNs, so by these active black holes at the center of galaxies.
Is there a limit, if I continually dump mass into a black hole, is there a limit to the point at how large the event horizon can be, or the amount of mass? Because there's a limit to a star, right? There's a point at which a star is so big that it can't get any bigger. Is there a limit to the size of a black hole?
So there's not really a limit because the size of the black hole is in a sense defined by its mass.
Right.
So if you make the mass bigger, so if you double the mass, you'll just like double its event horizon.
Right.
Did I say that right? Yes.
Yeah.
And so in a sense, by putting more mass, you just make it bigger.
Yeah.
The things that are limited, so black holes basically have three properties.
Yeah.
Which is why they're kind of boring objects.
Right. Until you get sucked into one. There's a point where it's not boring for a little while.
So there's the mass.
Yes.
There's the charge.
And spin.
And the spin. And so the mass, if you just add more mass, it just becomes more massive.
Yeah.
The size of the event horizon grows. But the spin is actually limited. Okay, so like if you try and increase the spin past a certain point, you won't be able to anymore because the spin is in a sense limited by the mass.
Right. Wait, how is spin limited by the mass? How?
So in the sense that there's an absolute bound on how high the spin can be.
Why is that? Is that because of the speed of light? Why is or is it because it could counteract the gravitational
in a sense,
pull?
if you have this maximally spinning black hole and you try to chuck more stuff into it, it just won't go.
Oh, it'll just push it out.
Yeah.
Okay, got it.
So, in a sense, trying to make these maximally spinning black holes seems to be fairly ubiquitous in the universe because when we go and measure the spin of black holes, a lot of them are very high spin. So you measure like spin in these absolute units. So like the highest it can be is 1, the lowest it can be is -1.
Yeah.
So it's like retrograde.
Yeah.
But a lot of them have spin like 0.9.
So when you eat the mass, I'm just going to use these layman terms. When you eat the mass of a planet or a star that comes by the black hole, you also eat its angular momentum, and that would add or subtract to the spin?
In principle, yes, but it's hard. So say you have like if I give a planet to the black hole, like it's hardly going to change its spin.
Yeah.
But if you have a more violent event, like say you merge two black holes,
yes,
in that way you can imagine growing the spin a lot. But in fact, if you have one of these mergers, it's not always clean. Like often you'll have a merger and the black hole will get kicked in some random direction. So you can bleed off angular momentum that way.
Yeah.
Just by having it, the merger product just like shoot off.
That's incredible. Okay.
So yeah, the physics of these kind of mergers is incredibly complicated.
Yes, and we talked about a merger when I went to go see. I don't know if you were there, but you invited me to one of the monthly talks they did at UNLV, where they talked about two supermassive black holes colliding with each other like 100 million years ago, and then
I totally forgot his name.
Gravitational wave.
He was a Northwestern professor.
Yeah. Well, he was talking about the gravitational waves that were created from two. You know what? Let's back up real quick. For those of you who are listening to the word black hole and don't know what the fuck we're talking about for a second, we were talking to our producer Travis here earlier. Is that you, Travis? I don't have my glasses.
That is me.
That is you. Okay. Sorry, I was gonna make sure I don't have my glasses on. We were talking to Travis before about acceleration, right? He was talking about acceleration in gravity, right? And when you have a level of acceleration, like on the planet Earth, acceleration is 9.81 meters per second squared. Well, just imagine that you continually increase that number until it got to 300,000 kilometers per second. Then that number would be to a point where light would not even escape. Is that pretty accurate?
So that's a good like hand wavy
Yeah.
explanation. So there's a concept of like escape velocity.
Correct.
Which is like, so imagine you want to launch a rocket, right? So you're on the surface of the Earth and you want to launch off the Earth's surface. You're going to need a certain amount of
It's
velocity.
11, it's 11 miles per second on the planet Earth.
Okay.
Yeah.
So whatever that number is, okay, that will let you escape the Earth.
Right.
Now, a black hole, okay, the escape velocity would be the speed of light.
Exceeds speed of light.
Right.
Can the escape velocity exceed the speed of light, or does the event horizon just get bigger?
So in a sense, that's the physics is actually incorrect for that explanation, right? Because so suppose you don't reach the escape velocity at the surface. So say you launch off the surface at 5 meters per second or whatever the number is.
Yeah.
Okay. You can keep on adding velocity. You can keep on accelerating.
Yeah.
Right. And then you could reach the escape velocity eventually.
Yeah.
Right. But with a black hole, no matter how much you're accelerating, the whole way you won't be able to escape.
Correct.
And so it's a good heuristic. So like a good way of remembering, like, oh, this is what a black hole means. If I had velocity equals the speed of light at the surface,
Yes.
I wouldn't be able to escape using Newtonian physics.
Yes.
But that physics is actually not correct
because of relativity.
That's correct.
Because all right. So just to go back to what we said before, 9.81 meters per second square on the surface of the Earth because of the Earth's mass and how far away we are from the center. If you kept increasing that number to a certain point, you get to a point where no matter would be able to escape, and then at that point, light would no longer also be able to escape because you have bent space time in on itself.
Yeah. So actually the picture that I have for like what a black hole is.
Yeah.
So imagine one of these like corn mazes.
Uh-huh.
Okay. So in a corn maze, right? There's like, if I go this way, I'll eventually get out. If I go this way, I'll reach the center.
Yeah.
Okay. Like a black hole is like, no matter which direction you go, they all lead to the center.
Yes.
Like that's the picture to have.
Yeah.
That it's not. It's like which way I go, how fast I go. It's like no matter which way you go, how fast, you're just eventually going to reach the center.
Right. Is this? I know this is a weird question, but is that a function of gravity, or is that a function of space time being bent in on itself, and like no matter where you are, you end up back at the singularity, or is it both?
Yeah.
Or do we not know?
Okay. It's really the second.
Okay.
It's that no matter which way you go, you're going to end up like towards the singularity.
Okay. And the singularity is the spot inside of the black hole that is hidden behind the event horizon that is infinite mass and infinitely small area. I forgot exactly how it's described.
Basically, so all this math that Einstein discovered
Yeah.
to explain all these phenomena
Yeah.
basically breaks down at the event horizon. So
Yeah.
it's basically at the center of the black hole. You basically can't calculate things anymore with this theory.
Yeah. Okay. So we just don't know. Yeah. I had a professor one time that told me butterflies were inside of a black hole, and he was like, because we don't know. It's like any guess is as good as ours because we don't know. Or the math breaks down, like you said before.
The math just breaks down, so you can't really calculate predictions anymore.
Okay. Interesting. Okay, awesome. And then what was from your I guess this is part of your thesis, the structure. What was the theory you came up with? What was your hypothesis from your doctoral thesis?
So the main thing I was working on were for these protostars.
Yeah.
So I was understanding how gas falling into the star affects gas that's being launched out.
Okay.
Okay. Because there's always this like interchange. So we were talking about like how angular momentum is conserved.
Yeah.
You can also kind of think of like energy is being conserved in these processes. And so if some gas is losing energy and falling onto the star, other gas gains energy and gets shot out.
Okay.
Okay. And that gas that gets shot out, we can actually see it with telescopes. Okay. These are called winds.
Mm-hmm.
And the winds we can actually measure with telescopes.
Okay.
And compare to these kinds of simulations that I was doing.
And we're looking at in this we're just looking at protostars.
And this we're just looking at protostars.
Okay.
Protostars are they're like less cool sounding than black holes, but they're in a sense more cool because we have actual nice data. Like we can take pictures of these systems, and you can actually see like the star and the disk edge on, and you can see the gas being shot out.
So